Hello everyone, welcome to Brain Blitz Audios. Today in this episode of JEE Main, we'll be looking at previous year questions of mathematics asked in engineering entrance exams in India. Today we're dealing with the chapter Sets, Relations and Functions. This chapter in mathematics deals with a set of elements and the relation between two or more sets of elements and special relations which we call functions. So in JEE Main, this chapter is very important and it's among the 20 odd chapters that students study for acing their exams. So without further ado, let's look at the first question of this episode. This question was asked in 2005. A real valued function f of x satisfies the functional equation f of x minus y equals f of x times f of y minus f of a minus x times f of a plus y, where a is given as a constant and the value of f of 0 is given as 1. You need to find the value of f of 2a minus x with respect to f of x. So how do we solve this question? So in order to solve this question, we will take x equals 0 and y equals 0. So when x equals 0 and y equals 0, we use this formula and then apply the values for x and y. So on the left hand side, it will be f of 0 minus 0, that is f of 0, equals f of x times f of y, which is f of 0 times f of 0, minus f of a minus x, which in this case is 0, times f of a plus y, here again y equals 0. So you have f of 0 as equal to f of 0 the whole square minus f of a the whole square, because a minus 0 and a plus 0 are equal to a. And when you multiply f of a twice, when you multiply f of a with f of a, you will get f of a the whole square. So now what we do is we take the value of f of 0 as equal to 1. So you have 1 equals 1 squared, that is 1, minus f of a the whole square. So basically now what you get is f of a the whole square is equal to 1 minus 1, that is 0. So since f of a the whole square is 0, you can safely write that f of a is also equal to 0. Now let's hold on to this value for a bit and then let's move on to the question asked. The question asked is f of 2a minus x. So we can write f of 2a minus x in the form f of a minus x minus a. So this makes it in the form x minus y. So you can use it for simplification, use the formula. So in this case, x is a and y is x minus a. So f of 2a minus x can be written down as, using the formula, f of a times f of x minus a, and then minus f of a minus x, which in this case is a minus a, that is 0. Or let's write it as a minus a. And then f of a plus y, which in this case is f of a plus x minus a. So over here, notice that the value of f of a is taken to be 0 because we managed to find that out. So f of a is 0 times f of x minus a, so that part will definitely be 0. F of a minus a is equal to f of 0, which is equal to 1, and you have f of a plus x minus a as equal to f of x. So it will be 0 minus f of x. So the value of f of 2a minus x is equal to negative of f of x. And this relation is used later in integration in order to look at certain integrals. for some special integrations. So this relation is very important. So in this question, the right answer is option B, minus f of x. Note that f of minus x may not always be equal to minus f of x, so option C is incorrect. Option A is also incorrect. And option D is incorrect because f of the value of f of a is equal to 0 and the other side is not in the term f of a minus x. So therefore option B is the correct option. Let's look at the next question. Let W denote the words in the English dictionary. Define the relation R by the statement R equals the terms x comma y belonging to W comma W such that the words x and y have at least one letter in common. So you need to find out whether the relation is reflexive, symmetric, transitive, or the other combinations that come with it. So over here, this question was asked in 2006. So here W is the set and the relation is R, x comma y belonging to W cross W such that the words x and y have one letter in common. So let's start off by proving whether this function is reflexive. So for proving that, it's a relation first of all, not a function, because over here it's given. It's the relation R, not the function. So in order to prove that a relation is reflexive, you need to prove that the element a comma a belongs to R. So suppose you have a word, say dawn, and then you take the same word again. So if you can see that all of these letters are present in common with each other, so therefore at least one letter is common in this scenario. So therefore x comma x belongs to R. That means the relation R is reflexive. Now for a symmetric relation, you need to prove the condition that a comma b belongs to R implies that b comma a also belongs to R. So suppose that we have two words, say dawn and nest. So over here the letter N is common to both. So if dawn is x and nest is y, then x comma y belongs to R because both of them have a letter in common, and y comma x also belongs to R because even if you interchange them, it's not going to dilute the property that both of them have one letter at least in common. So x comma y belongs to R, y comma x belongs to R. That means the relation R is symmetric. So you need to prove the last part, that whether the relation R is transitive. For proving that a relation is transitive, you need to prove the statement that a comma b belongs to R and b comma c belongs to R implies that a comma c also belongs to R. So now let's take x as the word dawn, D-O-N, and y as the word nest, as already taken, and let's take a word z. Let's say we can take the word she. It's not technically a word, it's just a pronoun, but the purpose will do. Now over here, x comma y belongs to R because N is common between x and y. And if you notice again, y comma z also belongs to R, because the letter E is common between Y and Z. But if you look at X and Z, X has DON, Z has SHE. But X comma Z does not belong to R. So that means R is not transitive. So there are cases where R becomes transitive, but it's not true for all cases. There are cases where transitivity of a relation can be disproved. So therefore, this relation R is symmetric, reflexive, but not transitive. So if you look at the following options here, option B will be the correct option. Option A says that the R is not reflexive and it is transitive, which is incorrect. Option C says that R is an equivalence relation, which is incorrect. And option D says that the relation is not symmetric and it's also transitive, which, as we have proven, is incorrect with respect to the given function. The given relation. So now let's look at the next question. The set S, comprising of the natural numbers 1 to 12, is to be partitioned into 3 sets A, B, and C of equal size. And the condition given is that A union B union C equals the set S, and the other condition is that A intersection B equals B intersection C equals A intersection C equals phi. We need to find out the number of ways to partition the set S. So this question is basically a one on combinations, but there are elements of sets which come into play here. So over here, the second condition says that A intersection B equals B intersection C equals A intersection C equals phi. Now what does that mean? Intersection of two sets means to write a set with the terms with the common elements. So if A intersection B is written as phi, that is the empty set, it means that there are no common terms among the three subsets, among the three sets. So therefore, there are no common terms present here. So in terms of combinations, if there are no common terms, that means the sets taken are not replaced. If they were replaced, then the combination, the idea of combination would be different. But over here, it's not replaced once a set is taken. So therefore, we can use that formula. So for this question of 2007, what we need to do is we need to take the set 1 to 12 and make 3 sets of equal size. And equal size means you have to have 4 elements in each set. So how do you find out the number of ways of choosing 4 elements for a set? So what we can do is we can use the laws of combinatorics here. So firstly, we have 12 elements in the set S, and we need to take 4. So therefore, the combination here is 12C4. And since the 4 elements taken are not replaced, the second time we try to take the 4 elements, that means to take a second set, will be 8C4. And the last one is 4C4. So just to let you know what happens here is that first we have 12 elements and we need to take one set out. That means 4 elements out, so 12C4. And once one set is taken out, you have 8 elements remaining. So the second set is taken using the combination 8C4, and the final combination is 4C4. Now, for a combination NCR, the formula is n factorial divided by r factorial into n minus r factorial. So for 12C4, it will be 12 factorial divided by 4 factorial into 12 minus 4, that is 8 factorial, times 8 factorial divided by 4 factorial times 8 minus 4, that is 4 factorial. Then you have the last one, 4 factorial divided by 4 factorial times 4 minus 4, that is 0 factorial, which is equal to 1. So over here, 8 gets cancelled, one of the 4's get cancelled. So what you have is basically 12 factorial divided by 4 factorial into 4 factorial into 4 factorial, which is equal to 12 factorial divided by 4 factorial, the whole cube. And this is the closest that we can get to a correct answer. So this is the correct answer for the question. So if you look at our given options, then you can see that option A is the correct option. In option B, there is the multiplication of 4 factorial extra in the denominator, which makes it incorrect. And in option C and D, there is a presence of 3 factorial, which makes this incorrect. Let's look at the final question for this episode. Let R be the real number line. Consider the following subsets of the plane R cross R. The set S is defined as x comma y such that y equals x plus 1 and 0 less than x less than 2. Seems a standard set. The set T can be written as x comma y such that x minus y is an integer. So we can write that as T equals x comma y such that x minus y belongs to the set Z, set of integers. We need to find out which of the following is true. So according to the given options, we need to prove that first we need to prove whether S and T are equivalence relations or not. So over here we need to prove the 3 properties, whether R is reflexive, symmetric, or transitive. This question was asked in 2008 and it can be quite complicated. So what we're going to do is we're going to take this set S first. So S equals x comma y such that y equals x plus 1, 0 less than x less than 2. Now for the relation to be reflexive, A comma A must be belonging to the relation R. So if we were to put x comma x, then S will be equal to x equals x plus 1. On the front, it looks absurd, and when you put x equals 0, it becomes even more absurd. So S of 0 gives 0 equals 1. This kind of a relation is not possible. So it's not possible at all. So therefore, the set S cannot be an equivalence relation. For an equivalence relation, a relation has to be reflexive, symmetric, and transitive in order to become an equivalence relation. So therefore, the relation S will never be an equivalence relation in this case. So if you look at our options C and D are incorrect because both of these options states that S is an equivalence relation, whereby it is not. So among options A and B, which of these is correct? We can look at that by taking the relation T. So T equals x comma y such that x minus y belongs to the set of integers. So for reflexive, a comma a belongs to R. So if you take x comma x, so in x comma x, t will be equal to x minus x, which is equal to 0. Now the set of integers contains the set of natural numbers, the set of whole numbers, as well as negative numbers. So therefore R is reflexive. I mean, instead of R it's actually T, so you can write T is reflexive. So far so good. Let's look at symmetry. For a relation to be symmetric, we should have a comma b belongs to R, implying that b comma a belongs to R. So let's consider x comma y belongs to R, and let's consider their difference to be some value lambda, and this lambda belongs to z. So therefore now you can write y minus x as equal to minus of x minus y, which will be equal to minus lambda. So if lambda's value is positive or negative, the value of minus lambda still belongs to the set of integers. So minus lambda belongs to z. That means y comma x belongs to R, which means that, okay, it's actually t, so my apologies. So you can write t in place of R. So you can write the relation t is symmetric. Again, it's proven to be reflexive and symmetric. What about transitivity? For a relation to be transitive, a comma b belongs to R and b comma c belongs to R, implies that a comma c must also belong to R. So consider x comma y belonging to t and y comma z belonging to t. So that means x minus y can be written as a constant lambda, and y minus z can be written as a constant mu. Lambda and mu belong to the set of integers. So x minus y equals lambda is equation 1, y minus z is equal to mu is equation number 2. So on adding equations 1 and 2, you will get x minus y plus y minus z equals lambda plus mu. So minus y plus y equals 0, so x minus z equals lambda plus mu. So since lambda is an integer, mu is an integer, their sum has to be an integer. So lambda plus mu belongs to z. That means x comma z belongs to the relation t. So the relation t is transitive. So the relation T is now proved to be reflexive, symmetric, and transitive. So therefore T is an equivalence relation. So in this question, by solving, we've proved that S is not an equivalence function and T is an equivalence function. So the correct option to show both of these ideas is option A, where it says T is an equivalence function on R, but S is not. So options C and D are already incorrect because they say S is an equivalence function, and in option B it says that T is not an equivalence function, so therefore option B is also incorrect. So that concludes this episode on JEE Main. We hope you found this episode interesting. For more useful and interesting content, don't forget to subscribe to our channel, which is Brain Blitz Audios. If you want to access more of our videos on JEE Main regarding regarding the chapter Sets, Relations, and Functions, you can always hit the link in the description down below. So, until the next webisode, take care, stay safe, bye-bye for now.